Okay, greetings aspiring scientists. Welcome to my lecture today on the line spectrum of hydrogen, continuing on my previous videos on our quest to understand electron configurations. So let's get right into it. Let's go to my slides. So this is 1.3.2 line spectra of hydrogen for the IB chemistry curriculum. Excuse me. So, what does the quantization theory mean for the atomic model? In my previous video, I introduced the idea of quantization, so something about the way that hydrogen emits and absorbs visible light radiation was not continuous, it was quantized. So last time I told you about how those spectra were obtained by passing light through various prisms and gases and things like that. You can watch my previous video to see that. But in this video, we're going to mostly consider theoretically how could this happen or what causes this. So you might remember if you watched my atomic structure video, Rutherford, after discovering the nucleus, proposed an atomic model kind of like this picture on the left here. A dense, positively charged, small nucleus surrounded by electrons orbiting around. But none of these electrons are different from any others. So it really was this emission spectra and absorption spectra of hydrogen specifically, I think, that led to the idea that these electrons probably are not all equal. These lines most likely represent transfers between energy levels inside the hydrogen atom. And if there's different levels and electrons can enter them, that means we need a model that has different energy levels, and that led to the Bohr planetary model on the right here. So this might be carbon. It has various different energy levels, n equals 1, n equals 2, n equals 3, n equals 4, all the way up to n equals infinity, actually. But yeah, you can see carbon has some in level 1, some in level 2, nothing in level 3 and beyond. But that doesn't mean that electrons can never go there in carbon. Electrons actually can, given a bump of energy, reach the higher levels. Alright, so let's look at hydrogen specifically. Forget about carbon for a while. So, the scientists who excited low-pressure hydrogen with heat or electricity would see these four lines. One near, looks like, 400, 420 nanometers, one around 450, one around 500, one around 670 maybe. So we've got a violet one, a blue one, a teal one, and a red one. So it looks like they start closer together and then get farther apart as we move to the right. So these lines represent a certain energy according to E equals hc over lambda. And that energy that they represent, I think Bohr's idea was that that energy represents gap between certain energy levels. And as the electron falls a certain gap distance between levels, these lines will be produced. And that was exactly right. So you can see on the left here, I've got where all these lines come from. Okay, so you can see actually these lines represent transitions between energy levels. See, as you go from n equals 3 to n equals 2, what would be a small gap, a small sort of distance to cover on my diagram here, that would be the red line, high wavelength. As you go from n equals 4 to n equals 2, that would be a slightly bigger gap. That's the bluish green teal line. As you go from n equals 5 to n equals 2, you get the more darker blue line, bigger gap. And as you go from n equals 6 to n equals 2, that's more the violet color, the lowest wavelength. And this was quite an amazing discovery. As you can imagine, these lines perfectly match with the idea that electrons are falling down these energy levels. So how did they get up in the first place? Well, that's where we had to excite them with heat or electricity somehow. So this slide, before I go into it, I want to just preface by saying this used to be a much bigger part of the IB chemistry curriculum. I've seen a lot less textbook content and exam questions about it, so just be aware this may not be such an important thing anymore, but I still think it's a really important thing for students to know. So scientists actually calculated the energy of specific atomic energy levels, not just the gaps, but the actual energy of the level itself. I think it was done several ways, through just data collection first, and then through combinations of various different constants like the speed of light and Planck's constant and permittivity of space. I think various constants, when they come together, can give us this equation. E equals minus RH times 1 over n squared. So that n is just like the energy levels in the previous slide I showed you. It can be 1 or 2 or 3 or 4 or 5 all the way up to infinity, but it cannot be anything else. It can't be 1.5 or 2.6 or whatever. Only integer numbers for those levels. Then RH is what's known as the Rydberg constant, specifically the energy version, the energy unit version of the Rydberg constant. It is 2.18 times 10 to the minus 18 joules. And so we can ask, what's the proportionality between energy and an atomic energy level, n? And it ends up being E is proportional to minus 1 over n squared. So that is going to give us a relationship like y equals 1 over x squared. You know that graph is a curve that approaches asymptotically the y and x axes. So that's also going to be representative of the relationship between energy and energy level. So why do we have this minus sign? This is a really important idea in both chemistry and physics classes and theories. So we can say that, empty space or a free electron not near anything, that should be a reasonable place to call zero, right? Nothing going on. But then as an electron approaches a nucleus, it's probably going to speed up and eventually stop. But when it stops, it's going to take you energy to pull it apart because it's attracted, the electrostatic attraction between positive and negative. So if you have to put in positive work to pull it away, then we can say that electron is at a negative energy. This is a really weird idea, but you can look at the picture I have on the bottom right here. This is not too dissimilar to things we experience on the macro scale either. We would often set height equal to the ground, right? 0. And we would put a ball there and say the ball has 0 height, it's at 0. But we could then dig a hole and give the ball a little shove and it can roll down. Now the ball is at negative height compared to what it was before. You have to put in work and give it positive height to get back to 0. Very similar situation here. An electron near the nucleus has kind of fallen in a hole, and something needs to push it out with positive energy and work to get it out. So it does make a lot of sense the more you learn about math and chemistry and physics, why a lot of these things are negative. It's because it's based on where we set our 0 point. And we need to set our 0 point as something that makes sense. Alright. So what exactly happens when an electron absorbs or emits a photon? When a photon of electromagnetic radiation is absorbed, h nu, the electron jumps to a higher level, and this is called an excited state. So that's not where the electron normally is in a normal atom. And this usually only lasts for a fraction of a second, and the electron then returns to its lowest natural regular state. That's called the ground state. And when it does so, it must lose the energy that it gained. And so it will emit its own photon. But that photon it emits is exactly equal to the one that bumped it up in the first place, the one that it absorbed. So the absorbed photon energy will always equal the emitted photon energy in the examples that we look at anyways. So h nu in, h nu out. Same wavelength, energy, and frequency. So you can see my little animated diagram from Cloud AI on the left. Our ground state in n equals 1 absorbs some energy, goes up to n equals 2, but very quickly will fall back down and release a photon of the exact same energy. Okay, but basically any transition is possible. 1 to 3, then 3 to 1, 1 to 4, then 4 to 1, all the way up to infinity. Alright, so we're not just interested in the energy of a specific level, but what we most of the time observe is going to be what's emitted and absorbed, right? And that is the difference between two energy levels. So that brings us to the energy equation for the gaps, delta E, difference between energy levels. So this will also be the photon energy of electromagnetic radiation that is absorbed or released. This must come from a difference in levels. So delta E equals RH, the Rydberg constant, multiplied by 1 over n initial squared minus 1 over n final squared. And because delta E is just an energy in joules, it can also be represented by h nu and hc over lambda. So your initial energy level can be anything 2 or higher. Again, it can't be halfway between numbers, just 2, 3, 4, 5, 6, all the way up to infinity. But it has to be higher than 1, right? Because you can't drop from 1 to 1. It has to be 2 to 1 or higher. The final energy level, though, can be anything as long as it's lower than the initial one. That's a key point. So here's a practice question. I think we'll only have one practice question for this because all of the practice questions kind of end up being the same. You just convert between energy, frequency, wavelength, those kind of things. So try calculating the energy difference between level 1 and level 2. Remember, the Rydberg constant is 2.1 times 10 to the minus 18 joules. And then what would be the wavelength of the photon released by an electron that makes that jump, either up or down? For that, you'll need Planck's constant and the speed of light, actually. So Planck's constant is 6.63 times 10 to the minus 34. Speed of light is 3.00 times 10 to the 8 meters per second. Both of those are in your data book anytime you need them. So let's go to the whiteboard for a minute to solve this. Okay, so we want to try to find the energy difference between level 1 and level 2. So, all right, delta E, the energy gap or difference between levels, is equal to RH. When we're checking for these gaps here, we no longer have a minus sign in front. Now, this is equal to 1 over n initial squared minus 1 over n final squared. N, not h, okay? So what are we going to say is initial and final? Maybe I'll say, let's imagine an electron is falling from level 2 to level 1. So my initial is level 2, my final is level 1. So I can put in my numbers. Rydberg energy constant, 2.18 times 10 to the minus 18 joules, multiplied by 1 over 2 squared, and minus 1 over 1 squared. So anything that involves level 1 is quite easy, right? Because 1 over 1 squared ends up just being 1. But you can put these numbers into your calculator. And you should get 1.635 times 10 to the minus 18 joules. Okay, what about significant figures? Well, the energy levels themselves are countable things. They have unlimited significant figures. So just going by my Rydberg constant, I'll try to set this to 3 significant figures minus 1.64 times 10 to the minus 18 joules. So that's the first part of that question answered. Why is it negative? Well, it's a change in energy, delta E, right? And we've gone from a higher level to a lower level. And I think what this energy represents is a potential energy, right? So just like if I was holding this pen high above the ground and then I let it drop, just like this electron is dropping, well, this pen has lost gravitational potential energy. And when it's on the ground, it essentially goes back down to lower potential energy. So our delta E here is a change, and it's a loss of potential energy. Okay, the second part of this question was, what would the wavelength of this photon be when it's released? So we have energy of a photon equals h nu equals hc over lambda. And what I'd like to know is lambda. So lambda equals hc over E. H was given in the question in the data book, 6.63 times 10 to the minus 34 joule second. And C is the speed of light, 3.00 times 10 to the 8 meters per second. All of that divided by our energy. I'll use my 4 significant figure version just because I'm not trying to report any answers yet. Minus 1.635 times 10 to the minus 18 joules. And you'll notice through the dimensional analysis of the units here, our joules will cancel out. Joule divided by joule is 1. And our seconds will cancel out. Second multiplied by 1 over second cancels out, and we'll be left only with units of meters for this answer, which is very handy and makes sense. You should always check that things make sense. So this comes out to about 1.2165 times 10 to the minus 7 meters. And I'll cut that to 3 significant figures, 1.22 times 10 to the minus 7 meters. Okay, that's fine, but photons that are involved with energy levels in this way are often written in nanometers, so I just like to write that this is 122 nanometers. 1 nanometer is 1 times 10 to the minus 9, so 1.22 times 10 to the minus 7 is 122 nanometers. But both of these answers are correct. This or this are fine. So 122 nanometers is actually beyond what the human eye can see. It's too short wavelength. It's in the ultraviolet range, so that's an important point as well. In the slide that I showed you of all the different colors, none of those went below 350 nanometers, right? So that's the range that we can see, but this one is too short. Okay, let's go back to slides. One thing I do want to say just before we move on is that the Rydberg constant is actually not in the data book, the chemistry data book, so if you would use it, the question would provide it for you, I'm pretty sure. Okay, so let's talk about these ultraviolet lines that are too short for us to see. According to the photon energy equation, E proportional to 1 over n squared, or energy is proportional to 1 over the energy level squared, gaps of energy between levels decreases at the same rate as a y equals Rydberg constant over x squared graph's slope decreases to 0. Okay, so the visible lines we looked at a couple slides ago are when electrons fall to n equals 2, but falling to n equals 1, you can see on this diagram here, is actually a much bigger gap. So n equals 1 would be represented by the red line at the bottom of this diagram on the right. So falling down that far is such a big energy gap that the wavelength is so short that we can't visualize it with our eyes anyway, but we have special detectors that can detect it, and I think this scientist Lyman worked on this series very much, these lines of ultraviolet light going to n equals 1 when the electron falls down to the first energy level in the hydrogen atom. And I've kind of drawn here this curved line that connects all of these energy levels. And you can see the gaps decrease as you increase in energy level. And this is kind of the same shape of a 1 over x squared curve. I've drawn that proportionality curve on the left. You can see the similarities if you just were to turn that and shift it over here. The rate at which these gaps decrease is the same as the rate at which 1 over x squared graph approaches 0. Now I could have drawn these lines with any spacing that I want, because the x-axis on this Lyman series diagram doesn't mean anything. It's just separated however much I want to visualize these lines. But still, I think it's a good visualization of the rate of decrease of that gap. Okay, so we've seen a visible light series to n equals 2. We've seen a Lyman series, ultraviolet. And you actually need to know the names of these and what they represent. So the Lyman series is n equals 2 or 3 or 4 or 5 up to infinity. It goes down to n equals 1. The region of electromagnetic radiation is then ultraviolet. Balmer series then is n equals 3 or 4 or 5 or 6, and so on, down to n equals 2. It's visible in a bit of UV. Then the Passion series is the third one you need to know. So you need to know the names of all these. The Passion series is 4, 5, 6, 7, 8, 9, and so on, down to n equals 3, level 3. And that will be infrared. The gaps become so small that the energy becomes so small, the wavelength goes up. And I think there are series beyond these, from n equals 5 down to n equals 4, and 6 and 7 and 8 down to n equals 4, and basically that can go on forever, right? It gets more difficult to detect, I think, as we increase these numbers, but still, they exist, but you only need to know these 3 for IB exams. And these series are only true for the hydrogen atom, let's make that clear. Alright, so some considerations. Question: if a perfect amount of energy corresponding to an energy level difference approaches an atom, what happens, assuming there's an electron in there? Answer: the photon is absorbed, the electron jumps to the new energy level. Absorption of a photon. Okay, what if a greater amount of energy approaches, greater amount than we need? Well, only the required amount to jump energy levels will be absorbed. The remaining energy passes through and likely will have a wavelength increase and a frequency decrease to compensate for that loss in energy. One exception, though, is if the energy exceeds the ionization energy. This is a special idea where the gap from wherever the electron is up to the infinity energy level, if we give the electron that energy plus more, in that case, we'll actually eject and kick the electron totally out of the atom, and any extra energy from our photon will go into the kinetic energy, the energy of movement of the electron, and accelerate it away from the atom. And then what if a lower amount of energy approaches? it cannot be absorbed. It will just pass through our material and carry on its way. One example of this is like glass windows, right? These do not absorb visible light. It just passes through and it can reach our eyes and we can see what's beyond the glass. Special property. Okay, so that's the end of 1.3.2, but I do want to just tag on 1.3.3 here at the end. It's only one slide's worth of information. So electrons in energy levels. What are some things we can say? So just to get into some quantum mechanics language, the principal quantum number, n, this is what we have been studying over the past 20 minutes or so. This defines the main energy level of a set of orbitals. Orbitals represent spaces where electrons can be, are likely to be, based on Schrödinger's model of the atom. This n number, the principal quantum number, can only be integer values, 1 or 2 or 3 or 4, all the way up to infinity, but cannot be things in between that, cannot be negative, cannot be 0. Now, the number of electrons that a main energy level can contain is 2n squared. So level 1 can have 1 squared times 2, 2 electrons. Level 2 can have 2 squared times 2, 8 electrons. And that will go up and up and up quite quickly. We'll get into why that is in my next video. Every time n increases by 1, a new sub-level type of orbitals becomes available. In level 1, we have one type. In level 2, we have that type plus another. In level 3, we have those types plus another. In level 4, we have those types plus another. Every time we go up a main energy level or up a principal quantum number, we get access to new areas where these electrons can be, which will become very important. They're labeled as S, P, D, F, possibly G, and so on. Okay, so we'll talk about that more in my next video. Thank you so much for listening. Hope you learned something, and hope to see you next time. That's all.